Hey guys, Miss Pipel here. Today in this video we are going to be looking at the steps beyond the Bohr model and what we've made in terms of advancements in the model of the atom since the Bohr model. So it turns out that Bohr's model didn't really work well for other elements. He only worked with hydrogen, and so the hydrogen is a super simple atom. One proton in the nucleus, one electron on the outside. There's not a whole lot of room for variety in that, and so his model was successful for hydrogen, but not anything else really. So again, he just focused on hydrogen. So Erwin Schrödinger was the next person to really start to think about the model of the atom and what atoms actually look like. And in his experiments and in his research, he discovered that electrons travel as waves and not really particles. But that also depends on the situation. So light and very, very tiny particles travel in very unique and intriguing ways. So when he figured out that electrons are moving differently than our normal understanding of motion, this opened up a whole new field of physics called quantum mechanics, which is referring to how very, very tiny things like electrons, part of incredibly tiny atoms, move. So the way that those move are very different than the way that when you throw a baseball or you kick a soccer ball, the way that that ball will move through the air. And so what he did from that information and from his new field of quantum mechanics was came up with a wave equation that was used to calculate the probability of finding an electron in a certain spot around the atom, or around the nucleus, I should say. So rather than finding the electron in these specific orbits, like Bohr said, Schrödinger said that we have these regions where we're likely to find electrons. They're not permanently there or permanently revolving around that nucleus, but they're likely to be in these certain locations. So we're going to look more at that in just a second. So why are we talking about probability, and why are we talking about the fact that it's not in these electrons are not in specific locations? Well, one of Schrödinger's students, Heisenberg, came up with this uncertainty principle, which really applies well to our electrons around the atom. And that says that you can't know both where that electron is and how fast it's going at the same time. So the more you know about the location of it, the less you know about how fast it's moving and the direction it's moving. And the more you know about its movement, the less you know about where it is. That is because these are such tiny particles and we cannot physically see them, right? So this is really a prediction based on calculus and mathematics that are beyond the scope of our class. So you kind of got to trust that Heisenberg and Schrödinger knew what they were doing. But again, so this is kind of pinpointing where they probably are. And due to this probability and the mathematical equations that tell us the likelihood of electrons being in certain locations, we have set up the model of the atom known as the quantum mechanical model. So quantum mechanics, remember, is how tiny particles move. It's the study of how tiny particles move. And so this is the model that tells us the likelihood of electrons being in certain locations, and that's what we're going to dive into for the second part of this unit. So kind of to summarize what exactly this means, so Bohr, the reason we stop with Bohr is because he was, his discovery of energy levels was a pretty big deal, because those are still very much a part of the current quantum mechanical model of the atom. But energy levels don't look like rings. They're not orbits around the nucleus. And then not all electrons in the same energy level have the same amount of energy, and we're going to see that in a little bit. And then again, we can't be 100% sure of where those electrons are. So rather than saying electrons are in orbits, this is a good vocab word for you to write down today, is electrons we now say are located in orbitals, which are just regions where we have a high probability, again, not certainty, but a high chance of finding that electron. Okay, we're not going to be doing Schrödinger's calculations. They're, again, way beyond the scope of this class, but that's what those orbitals are based on. This is what they generally look like. So there are 4 different types that we are going to see. We have S, P, D, and F orbitals, and they all are different shapes. And this is just given to you as an image with the different orientations, and those circles represent the probability, like those regions where those electrons are likely going to spend their time. So Schrodinger's model of the atom gave us this hierarchy of organization for electrons, and so that's what we're going to spend pretty much the rest of this unit looking at. So the first level of organization is called the main energy level, and that's just like the Bohr model. So just like you had, n equals 1, that was the first energy level, same idea, and we have energy levels 1 through 7. Then within that energy level, we have 4 types of subshells. Okay, so those are types of orbitals, the S, P, D, and F, which were the pictures that we just looked at. Okay, not all energy levels have all 4 types of subshells. Next, within that subshell, we have those specific orbitals. So specific orbitals are those regions where electrons exist. And then within an orbital, electrons can only exist in pairs. There are only 2 electrons in every one orbital. Sorry, you can probably hear my dog in the background. So if any of you have ever been to a suite-style dorm on a college campus before, that's actually an awesome analogy for how this electron organization works in our current model of the atom. So this is Ehringhaus over here. That's why I put that picture in there. That's where I lived at UNC, and that is a suite-style dorm. So how this analogy works is each floor on that dorm building is like the main energy level. So, I lived on the 6th floor, so I would take the elevator up to floor 6 every time that I got to my dorm. So that's like the main energy level. Then each suite had multiple rooms in it, but there was one door to that suite. And so let's say, for example, I lived in like suite D on the 6th floor. That would be like my subshell or the type of orbital that we have in our atom. Then within that suite, there were 4 rooms. And so I lived obviously in one of those rooms, and your electron is going to live in one of those orbitals. So that's the idea, where your room within that suite is like the orbital. And then the electrons within your room or in your orbital are like the roommates. So obviously there are 2 electrons in every one orbital, just like there are 2 roommates generally in every one dorm room. So I think this is a really good analogy. This picture over here kind of shows that like this is a room, this is a room, this is a room, and this is a room, and then there's one bathroom. So there were 8 people sharing one bathroom, which is always good times. But so this I think works as a really good analogy if you have ever been in a building like this, or if you can even start to picture it. So we will kind of explore this more in class and answer any questions you may have once we get back to class.